All right, let's quickly do a refresh on the different types of basic architectures for systems. The first one was an accumulator, where your processor always operated on a single register. So you had one register. You didn't have to specify that register because it was always one register, so it was pretty simple. You were always operating on the register. So if you load from an address, you know that that's going into the accumulator, the one address. You don't have to specify the register, you just load right into it. Add B, well, there's one register, so you're obviously adding a variable straight back into the accumulator. And then if you want to store it, nice. Same thing, you know it's coming from the accumulator, you store it back out. How complex is this?
Not very.
Not very. Is it efficient? Is it efficient?
That depends on what you mean by efficient.
No. What do you mean? What do you mean by that?
I mean, if all you want to do is load and store to one register.
So then when would this be a good idea?
Simple systems.
Very simple.
Yeah.
If it's an extremely simple system, this might be a good idea. Nowadays, with how our processing and our fabrication technologies, you're not going to see this very often anymore. The next one was a stack. This was interesting. You would push and pop variables, onto a stack. So instead of a register, you had an implicit stack. By the way, x86 still supports these instructions. So you can push A onto the stack, push B, so the stack is now AB. And then you just say add. Well, if you say add, you're obviously adding the top two elements and then pushing the element back on the stack. Gives you a little more power than a regular accumulator, but also has some performance issues, because what if you need to get a value that's way back in there? Now you got to load it back out in the memory, get that value, and then push it back on. So there's a couple of issues with the stack. Then of course came registers. This is definitely the most common and general approach. You have a small array of registers storage, maybe 8 registers, 16, 32. Or 32 registers. These are just different places to hold an integer. I call it an integer, a number. So then you could say C, C equals A plus B. Whatever the value in register A is, add it to the value of register B, and then store it into register C. You can do load from R1 into A, register 1, load into register 1 from address A, load into register 2, from address B. Then you could add different things as well as store them out as well. And this gives you a lot of power, because now you don't have to be searching down a stack, as well as you can keep multiple pieces of memory, information temporary in your registers. I'll call them a register machine, or a load store machine is another term that you may have used when you studied these. Okay, memory. We simply think of it as a big array of storage. More complex than ways of indexing the registers, because you may have gigabytes of RAM or terabytes, depending on your machine. Yeah, who would be doing that? Oh, the Macs. All Macs have terabytes of memory now? Okay, that's good to know. So A sub I, remember this is an array. User base plus the displacement of A may be scaled based on what the array is. Integers are 4 bytes, characters are 1 byte. A dot pointer, use the base plus maybe the displacement of the pointer. This is a record, so remember you have an object, it may have different fields. So A is going to point to the beginning of that object, and they'll know what to jump down to in order to get to the pointer. There's different ways to think of memory and how they're implemented. Let's see, addressing modes. This hopefully will be a refresher. You can add 2 registers. You can put the actual number inside the instruction. You can do a base plus displacement. The base is R1, jump over 100. Let's say register indirect. That's whatever's in that piece of memory. Again, you just don't have to do displacement. Indexed. Oh, that's if you want to add those two to get the value. That makes sense. Directly, because you actually put the number directly in there. Memory indirect. Ooh, I don't remember that one. I think that go to R1, and then you find the memory that's stored in that, and then jump over to that one. AKA pointers. And then auto increment, aka plus plus. There's actually a lot of different ways. You only really need the top two, but the rest of these may improve the performance of your application. But if you add the extra ones, then you have to add the hardware support for it, as well as design it properly. So there's some trade-offs. All right. Hopefully you talked about bytes, half words, and words. A byte is 8 bits. Did you talk about this? Never?
Yeah.
You know about a byte, Matt?
Very freshly. Yeah.
Very fresh.
Yeah.
So how many bytes are in a word?
4 bytes.
There you go.
That depends though, doesn't it?
No, not when we talk about it.
Oh, okay.
Yeah, 4 bytes. A word is always 4 bytes. Now, an integer may be 4 bytes or 8 bytes, depending on your language. But from an architecture, a word is 4 bytes. Half word is 2 bytes. Big Indian or little Indian? All right. Let's see if I get y'all back here. Why would you choose one over the other? Actually, what is Big Indian and Little Indian?
I know what it is because I have to look it up all the time, but I can never remember it's the way it flows, which direction, from left to right.
What's the most significant digit? Is Big Indian or Little Indian? Most significant byte? So 11 is the beginning. Big Indian is how let's see. Points to the most significant byte. Right. So Big Indian is the biggest one, ends with it. Not exactly the way we think of it. Points to the least significant. Well, no, this is saying the other way. I'm sorry. Big Indian is how we think of it. Little Indian points to the least significant byte. Why would you do one over the other?
If you read like right to the left instead of left to right.
There is really no reason. But do you have to choose one? Yeah, you have to choose one. And you have to stick with it. Otherwise, bad things are going to happen. But I have yet to see really a reason to do it one way or another, except for there has been a standard way of network data. So you may want to match how networks store their Indianness.
How did they do it?
I don't remember. I never do.
Doesn't sound like right.
It's not that
I look it
important.
up every time.
Yeah. That's why we have Google, right?
And everybody seems to want to do it different.
So non-word loads, so that's LDB, load a byte. So if you want to load a byte from position 0, and let's see, you're loading 1 byte into R3. R3 in this case is a 32-bit register. Maybe you would pre-fill it with a bunch of zeros. If you're trying to load the FF, but you might be doing a sign extend where you fill in the previous ones. Again, this is only loading bytes, not loading everything. Or you can make it 0 field with load byte unsigned. All separate instructions. Okay, alignment. Word accesses only addresses ending in 00. Right. So let me go right here to the example. Why, if you try and load a word R3 from position 002, why would that be illegal? Load word. Previously I was doing load byte. Now I'm doing load word.
Because it's a word.
And those end in 0,
It's a
0.
byte, not a word.
It's a byte, but not word. Yeah, but why would? Oh, so
You can't put
let's just say, for the sake of argument, this array continues on. So there's technically are 4 bytes. Come on, Matt, you got this. Starts with the C.
Cache.
Cache. So you have to align it to normally to keep it in the cache and for it to come in through the bus properly. It's actually usually a hardware issue. So normally, actually with x86 it does allow it. It just slows down your machine significantly. But you can try and enforce it, or how could you enforce it? You could try and enforce it with the trap or an exception handling routine and just stop the program if it tries to do something bad. Or you could say that when you do a load word, it just implies that you have these two, and then there's two zeros afterwards, or there's a zero afterwards, so that the instruction is always legal. So there's different ways to actually enforce this problem. But hopefully you can tell there's a lot of little itty-bitty, nitpicky problems that can arise from your architecture. So it's important to sit down and design and test it. Okay. Wow. Opcodes. Did y'all do muxes and ALUs and decoders, Bart, or was that some? Yeah. Sorry.
Yeah.
I'm just trying to make. What do we need to go over? Muxes, decoders. So with the mux, you have
Been through all that long time ago.
long time ago. All right. Well, it'll come back hopefully. So opcode is telling you what instruction you're executing: addition, multiplication, division. So you probably want to use a mux to say which operations are you going to, or which circuits you're going to activate or utilize, I should say. Be able to select an operation ALU, write to certain registers depending on it. Right, so how flexible the control is and how compact the opcode coding is. So depending, hopefully we'll get to this. Microcode, direct control of signals. This will become really obvious when you start trying to implement your system, your in-order simulator. Your opcode represents the control signals that come in. So when you have an add, you want these control signals on. When you want to multiply, you have these control signals on. You can make decode significantly easier with careful opcode selections, which will actually, if you choose your opcodes correctly, aka the exact numbers that represent an add and subtract, etc., you can make your decode a lot simpler. Control flow. You have conditional branches. We have to implement if statements and for loops somehow, right? Branch if equal, branch if not equal. Unconditional branches, jump to this location. A function call is sometimes handled in the hardware, sometimes not, depending on your architecture. Most modern processors do, because they'll say jump and load register of some sort in order to get to the function. And then afterwards they'll have which will then implicitly store all the registers in memory, all the temporary ones. And then the return will of course restore them when they come back. A trap is a specific OS call or exception. So if you're trying to make a write out to the screen, a user does not, I should say user should not have permission, because nowadays apparently it does. User should not have permission to do that, so there might be a trap or execution. And predicates, we will get to that a little bit more, but it's a type of way of doing if statements where you have a very simple if-else with only a couple lines. You can basically execute both predicates and then only commit the one that actually occurred. Okay, wow, we're just cruising here. PC relative addressing. Make linking code a lot easier. Let's see. That is, for example, your for loop. You go down to the bottom of it. You want to do a PC relative because you don't know what your PC is. You just say now you need to go back 20 instructions. That's PC relative. It makes linking a lot easier and figuring out what your PC, where you need to jump to. Indirect addressing. That's if you need to call a library, a virtual function, or a switch. In an in-order pipeline, hopefully you learn that when you do this type, it stalls the pipeline because it doesn't know where to go. And then out-of-order execution, this will become even more of a problem. There are some, unusual modes, simplify target. All right, you might have some offset or trap tempers as well. Processor's also going to have condition codes, flags, opcode, branch to target, or maybe a compare or an add will be inside your opcode to tell you, hey, look, we're doing compare or we're doing an add. Registers usually requires a specific specifier for it, but hopefully your opcode will tell you what that is. And then you have comparison. But all these are going to create a condition code, which is a special part of your processor that says whether the condition was true or false, or if some other condition is true or false. Right, Matt?
Right.
Right. All right. Y'all need to take a quick break? You still good?
Yeah.
Yeah.
Question though.
Yes?
What pages through the book would this line up with?
This should be,
It's in the syllabus or?
with this one, which is chapter 1's a review, right?
Hopefully.
Okay. This is actually, this is actually the review. Some of this is in chapter 1, a little bit in chapter 2, but most of this is the review of your undergrad.
Okay, cool.
The point of this is that if this is not familiar, you need to go research your undergrad book. Function calls. All right, whenever you do a function call, usually the hardware takes care of a lot of things for you because we call a lot of functions all over the place. Save PC+1 for when we're returning. Manage the parameters, aka store them off in memory. Allocate space on the stack for the new function. Jump to that function. Usually you just have a jump instruction. Simple approach, jump instruction plus other instructions, aka make the compiler spit that out. Or have a call instruction, have the hardware take care of it. Which one is faster? Oh, this is good.
Call.
So the call is probably faster, but what was now the trade-off?
More complicated to do.
Control.
Yeah, you have more hardware now, right? Which may slow down your processor or may not, depending on placement and layout. Also, you gotta design that call. Hopefully it doesn't have a meltdown vulnerability inside of it. But yeah, so there's a little bit of a trade-off here. Most modern processors have a call instruction because function calls are very, very common. Okay, roll the compiler. So the beautiful thing about a compiler, it makes the complexity of the ISA we design basically irrelevant or less relevant. So the compiler takes our C code and translates it into the ISA, aka the instructions that we want. And then the assembler takes it from there. This is a good thing because a lot of times a non-orthogonal ISA, aka a non-intuitive ISA, I'll just say for the sake of argument, is very challenging to use correctly with writing by hand. Register allocation is usually better left to the compiler heuristics. They're better at running numbers and figuring out what should be in the registers and what should be stored in memory. And then it's easier for complex semantics to lead to global optimization. All right, this is kind of a complicated way of saying what's in the red box. People are pretty good at optimizing 10 lines of code. If you give me 10 lines of code, I bet you a human would actually spit out more optimal code than a compiler in the large case. On the other hand, a compiler is always going to win if there's 10 million lines of code. There's no way. And even at probably 100 or 1,000, the compiler probably is going to flat out win, unless that person sits down for a very long time. So yeah, the compiler can really help with global optimizations and other things. All right. Now let's go ahead and